picking back up here. I don't know why it said maximum time reach, but unbelievable. Okay. So anyway, there's Venus. Any other questions on Venus? We're skipping Earth. Why? Next chapter is going to talk about Earth. So we're skipping Earth for now and going to Mars. Okay? Its orbital distance is about 1.5 astronomical units. So let's get our picture here again. Here's the sun. It's bigger than this, but here's the sun. There's the Earth. Mercury about here, Venus about there, Earth here, and then here's Mars. Further from Earth than Earth to Venus. By a pretty long shot. This is only 0.3, there's 0.5. So Mars is even further away. Way out there. Okay? Now, geologically active regions, okay? They say active and then say inactive. Okay. Meaning it still has not many active volcanoes, but it does have, say, Mars quakes and things like this. Not many volcanoes, but it does have Mars quakes. It has canyons. Wait a minute. What makes a canyon? Mostly water flood. We can't think of many other, what other kind? Or what? Okay. Gases don't move much soil. The what? On Titan? Okay, yeah, because Titan is so cold that it's a liquid. So, yeah.
I was just trying to give a variety than just one.
Yeah. Okay, but it has to be a liquid, but Mars is not that far away that it would have liquid methane far away from the sun. So these canyons have been there a long time. That indicates maybe there was once water on the surface of Mars. None that we've detected on the surface now. There are terraced plateaus near the poles. I can't tell you why, but there are those near the poles. And there are flat regions pitted with craters. Now, why do you think they may be pitted with craters? Okay, very thin atmosphere, the next bullet here. These are related to each other. Very thin atmosphere, but it's mostly carbon dioxide like Venus. But Venus is an incredibly dense atmosphere. Okay, and there is strong evidence for liquid water in the past, namely those canyons being one of them. Okay, we've had numerous space probes to Mars. Now, I don't find this a particularly instructive picture, but this is a picture of the surface of Mars, and it does seem like there could have been water flow around here. The way the rocks are carved out, just like water would carve them, those are the canyons, and it does look like it could go that way. Okay? They call it an angular uniformity. I can't even read that. Let's see if I can find it in the book. It's called Palink or something like that. The picture in the book is much clearer than this one. Okay? So there is Mars. Now, this picture is also in the book. Actually, this picture shows up on page 386 and that one on page 387, so they're reversed order. I'm pretty sure this is where something landed and made, did some experimentation there. That's why there's such a distinct pattern there. But Mars is called, and you already said it, Dave, what's his nickname? Mars. The color. Say again? The red planet. And actually, it was named Mars. Why? Anyone know that? Mars was the, I think, Roman god of war. Okay? Red, fighting, mean, whatever, I don't know. Because it was red. Okay. So, here are some of the, oh, yuck. They skipped all the Mars missions. Well, they got them, skipped them in the book, too. I can't believe that. I thought they had them in here. Oh, wait, I'm sorry. I was on the wrong page. They're right here in the book. Page 385. And if you look at this, we kind of outnumber Russia here. USSR anyway. They sent a lot there too, but there's at least one ESA, and there's also, surprisingly, the most recent one was India. India has a space program. I wasn't aware of that, okay? And they've sent something to Mars, okay? Now, this I find to be a very interesting picture. These are the four they're never lined up like this, but the four terrestrial planets. There's Mercury, there's Venus, there's Earth, there is our moon, which is almost as big as Mercury. There's Mars, we're coming close to that, yeah. And there's Mars, one of Mars' moons. I think it has two. That's probably the bigger one. Okay. Now this leads to something else we'll talk about next chapter. Our moon is the largest moon per planet size that you'll find anywhere in the solar system. I mean, by big time. Even though many of Jupiter's and Saturn's moons are bigger, the planets are so much bigger you would expect them to be, but our moon is significant compared to our size, whereas most of the moons are real small compared to the sun. Okay, so there are some of the representations. Example 15.5, if the noontime surface of Mars can reach as high as 20 degrees Celsius, now what would that be Fahrenheit approximately? About what we are here, 68 degrees Fahrenheit. We may be a little warmer than that, but not much. Okay? That's as hot as it ever gets on Mars, room temperature. Is that warmer or colder than a typical room temperature of 72 degrees Fahrenheit? Well, I just gave it away. 68 is exactly 20, so that would be a little bit cooler than 72. All right? Example 15.6, Mars' coldest temperatures is around negative 140 degrees Celsius. What would that be in Fahrenheit? Negative 220 Fahrenheit. Let's not go there, okay? It's cold. Really, really cold.
Mars is actually cold.
It's farther from the sun. And it has very little atmosphere, okay? Atmosphere sort of blankets us and keeps us a little warmer than we would normally be. With a very thin atmosphere, not much help from Mars. Okay. Then there's also there's a couple things here that I want to point out. It's an interesting read, but you don't have to do too much with it. It's a case study. Is it worth the cost to send things to these other planets? Yeah. No. Or did you say, do they or could they? Do they? No. We are barely figuring out whether there was any life form on Mars, meaning microbial, bacteria, viruses, but no advanced life. We've done any. We're not even sure that maybe there was any even microbiological life. May have been, but not very advanced at all. Human? No, nothing like that. It's too cold. It's not got the atmosphere for it. Couldn't support life. Anything that used carbon dioxide could live there, like they call it anaerobic bacteria that can live without the presence of oxygen. But no, there's no detected life at all, I don't think. Yeah.
Since you said Mars is somewhat geologically active.
Yeah.
So, I don't know if you like to get to this point, like volcano on Mars.
Yeah.
Olympus Mons. What happened if that volcano decides to erupt? I mean, how big would that eruption be?
Okay. Now, you're talking about a huge volcano on Mars. Way bigger than any volcano on Earth. Now, Mars is much smaller than Earth, but it has at least one, and I think a couple of really giant volcanoes. All it would do is squeeze stuff through the surface and come down the hill. I don't think it'd be anything major. It might mess up what little atmosphere it has for a while, but who cares? Nothing's living there. So, if major is anything happening on Earth, because that would affect life. There is no life there we know of. So it would just be, but everything sort of stabilized on Mars, probably more so than Earth, because it's smaller and not as major. Okay. Here's another sort of a dumb question. How fast will a rock falling from 60-meter high cliff on Mars be traveling when it hit the Martian surface? And they give the acceleration due to gravity on Mars of 3.8 meters per second squared. Well, that requires the math from the first half of the book that we haven't talked about. So let's just go to the answer. About 21 meters per second. Okay? And that says nothing to it. Okay? It wouldn't be as fast as coming from the Earth. Except for the other issue, Mars has very low atmosphere, so there wouldn't be as much slowdown because of, but 60 meters up, that's not very high. Okay. The next one's example 15.8. How long did it take a falling rock to hit the ground? And that would be about 5.6 seconds. For us, it would be considerably faster than that. All right, that's all they had on Mars. Let's move on to Jupiter. Okay? Now, what is between Mars and Jupiter? The asteroid belt. So here we have the Sun. Here we have Mercury, Venus, Earth, Mars. Jupiter is 5 times the astronomical distance. 5 times from here to there. That's 1, 2, 3, 4, 5. Somewhere around here would be Jupiter. Now the asteroid belt is somewhere between Mars and Jupiter. It's way out there. So remember those pictures that just showed them in the line? If you had those done properly, Jupiter would have been off the page. Where would Neptune and Uranus have been? We don't know. All right. So it's 5 astronomical units from the Sun. The most massive planet. 318 times Earth's mass. And Earth is a dense planet. 318 times that. Mostly hydrogen and helium with an iron silicate core. Now, most of these planets will have iron in their core, but most of the planet is made up of the gases. Now, that iron silicate core, who knows whether it's solid or liquid? I'm guessing it's probably mostly liquid because that's a lot of pressure on it, so it probably is liquid, but they don't ever say. But my guess it would be liquefied. Okay? Now, here is a cutaway view of Jupiter. There's an iron silicate core. Now that core, way down there, very small, is still 10 to 15 Earth masses. I mean, 10 to 15 masses of Earth in just that little core of Jupiter. Okay? 318 Earth masses in the whole planet, but 10 to 15 right in there. Now this is, they call liquid metallic hydrogen. And that is bizarre. Okay? On several fronts. One front is usually liquid hydrogen is in incredibly cold temperatures. But this is under incredible pressures, so it may not be that cold. So it's to have enough pressure to turn it into a liquid, and whatever they mean by liquid metallic, it's impressive. Now, I don't know how much they know about it, but that's what we think it is. And then outside of that, you have liquid hydrogen, and then an atmosphere that's hydrogen, helium, and ammonia. Again, ammonia is something I think of as coming from living things, but obviously it wasn't there. Ammonia is NH3, nitrogen and hydrogen. Most of the time, it's really been gross today, hasn't it? Ammonia, if you've ever smelled ammonia, you probably remember the smell. But that, back in our early history, when they didn't have much good cleaning supplies, basically rinse clothes out and bang them against rocks and things like this. The closest thing they had to a cleaning solution, urine, because it's high in ammonia. Okay? Huh? Urine. No, mine. No, urine. I'm not sorry. I was going to say I'm sorry. I'm not. Okay. All right. So there's ammonia out here too. I said it was a gross day, wasn't it? Okay. It must be gross. Okay. What we see is that atmosphere out there, but inside that you have a liquid hydrogen. Now again, that indicates to me cold temperatures, and it is. Way out there it can be cold, but it's also because of water pressure too. Okay. A lot of people have been getting up. Do we need to take a break?
Yes.
Okay, let's do a break. I wish, well, I don't mind that we started on. So let's pause this, and hopefully I'm going, no, okay. All right. So, we've hit the first slide of Jupiter. Let's go to number 2. Here is one of the key features of Jupiter, okay? This is called the Great Red Spot, okay? With a good, maybe pair of binoculars, but certainly with a telescope, you see this. It is huge. They think it's some atmospheric storm that has been happening for centuries, okay? It hasn't ever quit, okay? However, it does appear to be lessening slightly, okay? So maybe the storm's almost over after centuries of the storm, okay?
That is like acid rain.
What's that?
You saying that one storm lasted long?
Yeah, that's what I'm saying. Okay.
That's on Jupiter.
And but the thing is, you see, Jupiter is a very, it's all gas, so it's a very gaseous thing, and the temperature changes and things like this. This storm has been rocking along for a while, and it spins really quickly too. So that means on the surface there is that's a high rate of speed. So the winds are high. Again, it would be a very hospitable place. Unless you're flying a kite. No. Okay. Okay. I'm just kidding. You'd have no place to stand. Okay. So, it seems like there should be another picture here, but there isn't. Okay. When I said things are happening, they say it's a dynamic atmosphere, meaning blowing like crazy. Okay. Winds, storms, all sorts of things going on. Mostly hydrogen, helium, ammonia, methane, and water in their atmosphere. Okay? Not probably a lot, but it's there. And the Great Red Spot was what we were just seeing before. I think they show another picture of it here. Only not a very good picture. The Great Red Spot is going up there, and then this is a smaller white spot. Okay? It has a very large system of varying satellites, varying, V-A-R-I-N-G. Now, before I get off this, let's go back to the other picture. This is the Great Red Spot, and this is that whiter spot that you saw near it. That's probably a storm going in the opposite direction because of the, balancing each other out. One's high pressure, one low. I don't know. But that's my guess on it. So I didn't know why they changed and made it like this. The Great Red Spot's up there, the white spot there. Now, somewhere here in the text, they tell you a little something about that, and I can't find it now. Okay, here it is. It is the uppermost ammonia clouds, perhaps mixed with sulfur and organic compounds, that form the bright orange, white, and yellow bands around the planet. You see them better in this shot. All those bands. varying things of whether ice or ammonia or other things like this. The banding is believed to be produced by atmospheric convection, in which the bright, hot gases are forced to the top, and where they cool and then darken in color and sink back to the surface. So basically, this would be a colder area, this would be a hotter area. So this may be a high pressure area, and that's a low pressure area. And the band's the same type deal. Okay? I don't know if they know for sure, but it's pretty, it's an incredibly active planet. Okay? Now, when it says a large system of varying satellites, that means moons. Okay, let's see if I can get here. It says Jupiter has tens of moons. Some of the smaller and yet to be discovered. The four brightest and largest can actually be seen by Earth with a good pair of binoculars. And those have a special name. Now, when it says tens of moons, I'm pretty sure that's into the 50s and 60s, maybe even 70s. It's an enormous number of moons. Okay? Now, again, some of the smaller ones may not have been discovered yet, so it may have even more than that. It's amazing. Okay? Here, say again? Don't want what? No. There's no solid surface is one thing. It's frozen, not frozen, liquid hydrogen on the surface with an atmosphere above that. So there's nothing solid. Yeah. Not in our solar system, no. In other stars, around other stars, maybe. People speculate there's got to be something. But here's what I consider. We're in a near circular orbit, and just that little bit of tilt that we have, 23.5 degrees, that makes our temperatures vary from the polar temperatures, which are incredibly cold, especially in their winters, to incredibly hot right around our equator. If we were tilted a little more or a little less, if we were a little closer to the sun or further away, I'm not sure we could live here. Okay? And that's why your question, is this good or bad that we're getting warmer? We're a pretty fragile planet. We may not be able to adapt to changes like we see happening. We don't know. That's the problem. Something happened back that wiped out the dinosaurs. Now, they think that may have been a collision with an asteroid or something like that, and they just couldn't adapt to a fairly minor change. And so they all died off. Now, that's theory. No one was that back there, and we can't reproduce it. So if we are that fragile, and then too, remember this, our atmosphere is just right, okay? It's just right to block the harmful radiation coming from the sun. There's tons of gamma radiation, X radiation, all sorts of stuff that would fry us in an instant. But our atmosphere blocks that. But then our atmosphere is just dense enough to keep some heat in so we don't get too cold. Now, can any place come up with just this right combination to support life as we know it? It seems like it's a pretty tall order, okay? For all the things, all the trees we have to be putting out enough oxygen to sustain life. And what's really scary to me is that in Brazil, where they've been burning their tropical rainforests so they can get new farmland, hey, that supplies most of the oxygen that we use. And at some point, we may get out of balance there. And then the wildfires they've been having in Australia, you know, this is scary stuff going on. I don't know whether it's good or bad. It tends to be toward bad, or it's getting warmer. Yeah, I like warm weather, but not at any cost. Here are those four largest of the moons. Now, why are they called the Galilean moons? Do they have anything to do with the Sea of Galilee? No, absolutely not. Why would they call them the Galilean moons? Any ideas? Yes. What's that? Oh, I can't hear. So. Yes.
I say you just something simple like they in the galaxy and then the moon, basically.
Okay. Okay. It has nothing to do with galaxies. Here's what it has to do with. Way back, there was a very famous scientist who started really the scientific revolution, I think. And he heard of this other scientist up in Northern Europe who had developed a telescope. It wasn't a particularly great telescope, but he found out about it. So he started working on building him one. He made such incredible improvements in this telescope. He used it to look out at the night sky, happened to catch the planet Jupiter, and saw these 4 moons around it. Anyone want to estimate what that scientist's name was? Galileo! That's what the Galilean moons are named for, Galileo. Now, let me get them, I hope in the right order here. Okay, from left to right, top to bottom, okay? The first one, that next to the smallest, is EO or IO, I don't know how you pronounce it. The next one is Europa, that's the smallest. Ganymede is the largest, and then Callisto is, wait a minute. Yeah, Io, Europa, Ganymede, and Callisto. Io and Europa, okay, the two, okay, yeah, the first two, Io and Europa, are about the size of Earth's moon. Okay, these two are about the size of Earth's moon. These are not much bigger than that, but they are bigger than our moon. Okay, Ganymede and Callisto are slightly larger than Mercury, the planet Mercury. These two are bigger than Mercury. There's 2 of the moons. Yeah, it is. Okay, I was afraid you were going to say that. Okay. Let me mark the roll again, and before Miss Lewis gets out of here. Okay. Just kidding. Okay, we still haven't seen Bridget Michelle Cockrell. All right. Do we still have Brianna here? Yes, we do. Jerome is still here. Yes, he is. Aisha's still here. Jacob's still here. Kaya hasn't made it in today. She didn't make it in last time. Does anyone know? Second? Dudley. Okay. Rakiria is still here. Justin is kind of here. No, actually he's here. Okay. Shalanda is still here. Parsha is still here. Telling me what time it is. Okay. Eric is still here. Zach is still here. Katie didn't make it in today. I think, like I said, she may have the flu or something. Randy is still back there, I think. Okay. Miss Lewis is still here for a moment or two. Okay. Antonio, did we lose Antonio? Wasn't he right behind you?
Yeah, he was right there.
Oh, his stuff's still here? Okay. I won't, okay, I'll watch for him. David is still here. Tiffany is still here, mostly, okay. Kaylee is still here. Wait. Yeah, right there. Donald is still here. And Kaya is not here now, but her stuff's here, right? Okay. All right, I don't think we've lost anyone yet. We'll see if these other two make it back. All right, so there are the 4 Galilean moons. 2 of them about the size of Earth's moon, and 2 of them larger than Mercury. Amazing. All right, now here's the other thing. Remember, our moon is in the same ballpark as these, especially the top 2. And yet our Earth is about 1/400th the size of Jupiter. So you see the Earth to moon ratio of the Earth or moon to Earth ratio is huge compared to any other. Okay. Now let's move on to Saturn. Oh, wait. Here's a little exercise example. Assume one of Jupiter's moons receives a peak solar energy in a 10-hour period. How much energy is heating 1 square meter of the surface of Jupiter's moon during that peak time? Who cares? Okay. Now, if you got your book, or when you get it, and you see this figure here, we're going to talk about this figure later in the chapter. This is a really incredible shot, so I want you to sort of keep it in mind. Okay? Anyone want to make a guess of what that's a picture of? Okay. Hang on, we'll get there. Okay? And I think it's later in this chapter too. If not, it'll be in the next chapter. Okay, but I think it's later in this chapter. Now, here's another example. Oh, no, okay. The other one, it said, how much energy is heating 1 square meter of the surface of Jupiter's moon during the peak time? 2.9 times 10 to the 7th calories. What does that mean anyway? Never mind. Okay, interesting question exists regarding whether liquid water could exist on Europa, which is one of Jupiter's moons composed of water ice. Consider a 20 centimeter, blah, blah, blah. It goes on. I won't go into that because I don't even think it gives an answer. Oh, yeah, there's an answer. Okay. Let's move on to Saturn. All right. I'm going to have to adjust my scale here, I think, because remember we had this being the sun. Somewhere right about here would be Mercury. Right about here would be Venus, then the Earth, and then Mars about here, and then Jupiter was somewhere here, and then Saturn is almost as far from the sun to Jupiter as Jupiter to Saturn. It's about twice as far as it is to Jupiter. So, I mean, it's not just, they're not lined up. They are way stretched out. I mean, incredibly stretched out. So those pictures, I said the dimensions weren't right. Relative sizes were not bad. The dimensions were nowhere close. Now, let me also say this. Most of the four gas giants have rings. Most of the time, they're very small and hardly noticeable. Saturn has the beautiful rings, the very noticeable rings. So it's always drawn with that, and Shikaya is here. Okay. So we're still missing Antonio. That's the only one we lost recently anyway. Okay. So, way out there. The rings are particles. They don't go into detail in your book a little bit more of what those particles could be. It could be dust-like particles. It could be ice crystals, it could be other things. But the incredible thing, and I mentioned this in the table, it is 7/10 the density of water. The entire planet is 7/10 the density of water. Meaning if you had a pool of water big enough, which I don't know that it exists, it would be floating. Okay? It would not sink. The surface is similar to that of Jupiter's, which means it's a liquidy type surface with an atmosphere above it. And here they mention 30 satellites. Okay? The biggest of these, and this actually may be bigger than Ganymede and Callisto. I don't know, but I believe it is. You seem to know something about Titan. It's the only moon with a substantial atmosphere. Okay? But it's so incredibly cold, I don't think there's any chance that there could be any life out there. Okay. Now, the slideshow doesn't say anything about it, but I want to say something about it. There was a international mission sent mostly from the European Union, though we participated in it some. It was the Cassini-Huygens mission, and it took incredible pictures of Saturn and its rings and things like that, and it got more information we had ever had about Saturn. Anything you read and study about Cassini-Huygens, there could be probably several paper topics in that one mission, okay? Now, there is a figure in the book that doesn't show up on the slide set, so I want to show it to you now, but when you get your books, you can read it. Here is Saturn, and they name some of the rings here, the D ring, the C ring, the B ring, the A ring. They don't have any O ring. No, that's something else. Okay, here's an F ring, you know, there's various things here. And they don't go into detail any of this, they just name a bunch of the stuff. And it does list some of the moons out here, but Titan is way out there, okay? And also three other moons are listed. Rhea is listed there, Dion here. Now they never line up like this. You know, this is not an actual picture. This is a drawing, okay? There's Mimas, Enchiladas, that sounds like Mexican food. Tethys, Dion, I think she was a singer, and Rhea may have been, I don't know. But anyway, Saturn has quite a crowd around it, okay? And let's see, anything else they want? Oh, here's, I think, from Cassini-Huygens. I think this is one of the photographs they took of some of those rings. And aren't they incredibly beautiful? Okay. Now, any questions on Saturn? Okay. Now we go to Uranus and Neptune. And we really got to adjust our scale here. So let's do this being the sun. Let's put the Earth right here. Okay? That means Mercury's here and Venus is there. Okay? Mars is about there. Okay? Somewhere here is Jupiter now. Double that, and you've got Saturn. Okay? Double that. Oh, I made it too short, didn't I? Somewhere way out there is Uranus. Okay? Way out there. And where is Neptune? It's probably almost it's way, way, way out there. Now, you see why I say if there is another planet out there, how do we ever be able to see it? Because it's so stinking far away. Okay? Way, way far away. We depend on the light reflecting off of the sun's light reflecting off the planet. It's so far out there, it would be so dim it's lost in the sauce. Okay? But they have detected features of it, like gravitational things, so somewhere they're out there. These are the outermost giant planet, the gas giants, very similar internal structures to each other. They are very similar to the other gas giants too, but just a little smaller. And like I say, if every planet is almost doubling the distance from the previous planet, the next one would be about 60 astronomical units away. That's almost a Tuscaloosa. No, I'm just kidding. Yeah, it's way out there. Now, this is a picture of Uranus, I think. No, it's Neptune, I believe. Okay? Observed by the Hubble Space Telescope, and you see it is so faint. If you were about twice as far from the sun as this one, you would hardly be able to pick up an image. Okay? Actually, this looks more the color of Uranus, but yeah, it's hard to say. Now, let me go back. This is a more recent picture of Uranus, and this is probably the only reason we know its axis is tilted toward the sun, because you can see that little ring around it, and that means its axis is this way, where the sun is that way, and it seems to be spinning backwards, but how can you tell which is forward and backwards except by the direction of it? And it's just really bizarre. But it's so far out there, it's not really paying much attention to the sun at all. And then Neptune would be this. And that's, like I said, observed by the Hubble Space Telescope. Nearly the same size as Uranus, more than twice as far away from the sun. I don't quite say that. That doesn't pan out with what they're doing here, but it's pretty close. I don't know if these examples are even worth mentioning. The sun's brightness at Earth's distance is 1 times 10 to the third watts per meter squared. You're using inverse square relationship. How bright is the sun at Saturn? 100 times further away from the Earth. That would be, whereas the other was 1,000 watts per meter squared, on Saturn it would be 10 watts per meter squared. Pretty small. Which planet would experience the sun's brightness at only about 1/400th what is observed on the Earth? And that would be Uranus. So what would it be for Neptune? I would say on the order of 1/600 to 800th what it is on Earth. Incredibly small amounts. All right, now we're ready for the small bodies of the solar system. Oops, went too far. Now, let's name the small bodies first. There's the comets, then the asteroids, and then I don't like that they call them meteorites. This should be meteoroids, and we'll see why that's the case later. This is a misnomer here. Comets, asteroids, and meteoroids, not meteorites. Now, where do all these little things come from? Well, they're basically left over from the solar and planetary formation. We'll talk about this a little bit later in the chapter. And remember when the sun was forming, it was, had a lot of activity going on. There were probably explosions that blew stuff out, and that stuff later coagulated and became planets and asteroids and all this other stuff. So that's what they mean, left over from the solar and planetary formation. The sun was made and blew stuff out, planets picked up most of that stuff, or a lot of that stuff, then the rest of it is just out there. Now, here's the statement that I said be very careful about. The mass of the smaller bodies may be 2/3 of the total solar system mass. What does that contradict? Remember that statement right at the beginning of the chapter? The sun is 700 times bigger than everything else put together. So what they mean here, the mass of the smaller bodies may be 2/3 of the total mass, solar system mass, excluding the sun. We're not counting the sun in this, but if you take all the planets, all their moons, all of that kind of stuff, then this rest of the bodies out here are twice as much as that. Jupiter is huge, but and these are all tiny. So what we're talking about is lots and lots and lots and lots of tiny materials. Okay? Now these bombard the larger objects. Okay? Now remember the picture I showed you before? There it is again. What is that a picture of? There was once upon a time a comet named Schumacher-Levy. Now I think it got that name because two people saw it about the same time. First discovered it. Schumacher and Levy. Or maybe they were working together and saw it. I don't know. But anyway, remember it's a once upon a time deal? This silly little comet happened to get too close to Jupiter. And what did Jupiter do? Yank it out of its orbit and pull it into the planet. These are the fragments of that comet deteriorating in the atmosphere of Jupiter. Okay? This happened back in 1994, for any of you born then, maybe you got hit. Okay, so it would have burned up. Yes, it would have burned up because it was going in. incredibly high rate of speed, and that would have been very hot on a very cold planet, so it showed up like crazy. Now, what's hard to see here, I think I picked it out in the text once, but I can't see it in the projection. I think it's something along right around here is this. One of these is ultraviolet and one of them is optical. And so they probably look different colors, but just different filters they have. Would anyone know the name of the famous astronomer that discovered this? There was no famous astronomer that discovered this. It was a guy who liked looking at the solar system, the night sky, with his regular, probably a pretty nice telescope. And he looked and he saw this one night on Jupiter's surface. And he took a picture of it somehow, however he did that. And he sent it to something and said, "What is this? I've never seen this before." And it was like the national, NASA or somewhere like that. And they said, "I don't know, we've never seen it either." Okay. And then they went back and started figuring out, and they figured out, hey, that's about the time that Schumacher-Levy should have been going fairly close. Whoops, they got too close. Comet Schumacher-Levy does not exist anymore. There it was. It was discovered by a second.
Comets are made of gases and water.
Yeah, and rocks and things like this. We'll talk about those very shortly. So it doesn't exist anymore. This was first seen by an amateur astronomer. No famous scientist, amateur astronomer who liked looking at the night sky. Okay. So that's what happened. So let's look at where comets come from. Now these are in reverse order here. This is the Oort cloud. These are origin of the long period comets, those greater than 200 years. Now, where are we talking about? From 30 astronomical units to a full light year away. I don't remember how many astronomical units are in a light year, but there's a lot of them, okay? So this is, remember Neptune is out there around 30 astronomical units from the sun. These pick up somewhere outside of Neptune and go many times further, okay? Now, if you think about that in a three-dimensional globe, you're talking about a whole lot of space. And there's a bunch of comets out there. They're tiny, they're small, but that's why they can have so much mass. Okay. Closer in, but not by a lot, is the Kuiper belt, or some people I think call it Keeper belt. Okay, the origin of the short period comets, these are those that come around every 2,000 years or less. This is a disc-shaped region between 30 and 100 astronomical units from the sun. The Oort cloud is three-dimensional. This is a disk. This is three-dimensional, and that's from 30 to a light year away. So to answer your question, the solar system, I think it was her question, Aisha's question, was how big is the solar system? About a light year. Huh? Was that your question? Okay, about a light year in diameter. Not much out there, but it incorporates all that much. Whoa, that's a long way. Now, what happens, these things are out there. Now, some of them may be following really elliptical orbits, those in the Kuiper belt, but in the Oort cloud, they're just hanging around mostly. But every now and then, something will happen. Maybe two planets line up, or something happens, and gravitational nudges deflect the objects toward the sun. Now, once they start moving toward the sun, they start picking up speed, and then they go around the sun relatively close compared to where they were, and then get flung way back out there again. That's what happens with comets. They're very elliptical orbits, okay? And some of them are regular and some not. Now, here's an incredible illustration. Okay? Do you see the distance between the blue here? I can't tell any difference. Expand that up, that's the entire solar system as we know it. With the sun in the middle, this is Uranus, this is Neptune, and there's Pluto. The closer planets are all in there. They didn't even show that. Okay, that's this right here. Okay, that's that right there. This then would be the Kuiper belt. This band that goes around here, and this would be the Oort cloud. Now, some of the Oort cloud is within the Kuiper belt, and some is way, way beyond. But this is why everything, not counting the sun, but everything else within the solar system that we think of with the planets and stuff, that is about 1/3 of the mass, and then out here is 2/3 of the mass. Yes.
Is that an actual picture?
No, this is an artist's rendition of that. We've never sent anything out that far that we could get that. No. How do we know it? It's our best guess. Okay. But they have data to support it. Okay. And if you find this in your text, you'll see what those units are. They're just amazingly large. Now, I think someone also had the question, maybe it was also Justin, that if you're out here, the sun would be not much brighter than the other stars. Possibly. It seems like it would have to be somewhat brighter, but it may be that you can't really see it because it's in the middle of everything else. Okay. So I don't know. I don't know how accurate that rendition is, but it's not an actual picture. Okay. So these are comets. This is where they come from. The Kuiper belt, from Neptune to about 3 times Neptune's diameter, and the Oort cloud from Neptune to many, many, many times further. Okay. Yeah, question? I can't hear you. Leave it. Okay. Is that what you're saying? Okay. So what are we? We are some little speck of dust right in there. Okay. Yeah, I mean, just and this is just our solar system. One star out of billions of stars in the Milky Way, and then there are billions of other galaxies out there. We are less than a speck of dust. It's just incredible how massive we're talking. Okay, everybody got it? Okay, now to Jerome's question about statement about what comets are. They're small, solid objects, pretty much. Okay. One model is that of a dirty snowball, which is pretty descriptive. Okay. So frozen water, probably also frozen carbon dioxide. Does anyone know what we call frozen carbon dioxide? Dry ice, exactly. Okay. It's really cold stuff. Frozen water, frozen carbon dioxide, probably frozen ammonia, and probably frozen methane. Now, some of that may be heated up and become gas, but most of it's frozen. Now, that's the snowball part. The dirty part, there's dusty and rocky bits all over mixed in there, too. Okay? So, yeah, it's snowball. I mean, it's ice, but it's also dust, it's rock, it's a variety of things. Now, a comet is usually, when we see a comet, it has a head and a tail. Okay? The head is a solid nucleus and a coma of gas. Now, what I mean by coma is a surrounding of gas. Sort of like the Earth and its atmosphere. Okay? Solid nucleus and then a coma of gas around it. Now, the second part is the tail. And here we have Antonio. All right, everybody at least has been here in the second half that was here in the first half. All right, 2 types of tails. One type of tail is ionized gases. Now, what do we mean by an ionized gas? You want to know that? That's